and welcome to Cambridge Chemistry channel with sarwatahmed. Be sure to like the video and subscribe. This really helps the channel to grow. Today I will discuss transition elements. You know that in periodic table central block element is known as transition metal. For example, this is skeleton of the periodic table. Group 1, Group 1, Group 2, Group 3, Group 4, Group 5, Group 6, and this is and 7 group. This is Group 7 and this is Group 8. So this is the skeleton of the periodic table. So according to the orbital suborbitals distribution, this is the this is S block element, this is D block element, and this is P block element. So this is the distribution of the elements according to the electronic configuration, and you know, and these are the transition elements. So that's why transition elements are called as D block element. D block elements. Why it is D block elements? Because D block elements are the ones in which the last electrons enters a d orbitals during the process of orbital filling. The 10 element in the fourth period from scandium to zinc. So these are the scandium till zinc. So from scandium to zinc are members of the 3D series. These are the member of 3D series, like scandium till zinc. So in addition to the 3D series, there are also 4D, 5D, 4D series as well as 5D series, but these are not in syllabus. So we will discuss only 3D series, which are over here: scandium, then titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So from 21, this is 21, 22, 23, 24, 25, 26, 27, 28 and 29 and 30. So these we will discuss only these transition elements in A-level syllabus. Transition elements can be defined as transition element can be defined as elements are D block element forming one or more stable ions with partially filled d orbitals. So all the transition elements are D block elements, but not all. All 3D series are transition elements except scandium and zinc. So this is very important to know that scandium and zinc are not transition element. Because answer should be as they do not form any ions having incomplete d orbitals. So rest all elements like from vanadium to copper, they all form ions with incomplete d orbitals. So let's discuss the electronic configuration of transition element. 1 1 2 3 4 5 6 7 element, atomic number Z, symbol and electronic configuration. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So the atomic number is 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. Symbol is Sc, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Electronic configuration is like these are the four period elements, so electronic configuration will be written like this. Scandium I have written with yellow and I will explain the reason later. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 2 and 4s1. So I will explain this later. Titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d2 and 4s2. Vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d3 and 4s2. Again I have written with yellow 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 3d5, 4s2. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 3d6 and 4s2. Similarly 1s2, 2s2, 2s2 p6, 3s2, 3p6, 3d7 and 4s2. Nickel is 1s2, 2s2, 2p6, 3s2, 3p6, 3d 3d8 3d8, 4s2. And again I have written copper with 1s2. We have discussed earlier in AS, so later I will explain this after doing this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d 5, 3d9 and 10. This is 3d10 instead of 3d9, and 4s1, and this is the same as a pattern: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2. Why electronic configuration of copper? Why electronic configuration of scandium, chromium and copper are different? So scandium, like I have written only fourth period, 3d and 4 period. So scandium is, so this is the d orbital, so only 1 2 3 1 2 3 4 and 5, and this is 3d and this is 4s1 and 3d2. And similarly chromium, one two three four 5, chromium is 3d5 and 4s1. Similarly copper, 3d10 and 4s1. 1 2 3 4 5. The reason is this, like the electronic configuration of chromium, copper and scandium are unusual relative to those of the other transition elements. Chromium continues to complete the 3d orbitals. So instead of writing 3d4, I have written 3d5 and 4s1. So this is due to the uh, chromium continues to complete its 3d orbitals with unpaired electrons at the expense of the 4s orbital. Hence it requires the more stable electronic configuration like 3d5 4s1 instead of 3d4 and 4s2. So this is the most stable electronic configuration because this is unpaired, this is continue to half filled orbital, so one is left. So uh, this electron is jumped to this lower orbital. So this is the rule that we have to fill the lower orbital first, then the higher orbital, even though there is no such difference between 3d and 4s orbitals. So similarly uh, in case of uh, in case of coppers, Likewise, copper completes its 3d orbitals and expands of its 4s electrons to acquire the stable electronic configuration 3d10 4s1. It would appear that there is a special stability associated with the half filled and completely filled orbitals. So that's why copper is filled 3d10 4s1 instead of 3d 9 and 4s2. Hope you will understand this concept. Next is we'll discuss general properties of transition element. So if we compare the S block and P block metals, then there are certain difference between the S block metals and D block metals. For example, if we compare S block with D block metals, then we know that S block elements have low melting point and boiling point, while D block elements have high melting point and boiling point. S block elements are soft metals, is group 1 easily cut with knife, soft metals, but these are hard metals. S block elements show fixed oxidation state, like group 1 carrying +1 and group 2 carrying +2. But transition elements have variable oxidation state. Variable oxidation state mean more than 2 charge. For example, we know that this is common example, iron 2 positive and iron 3 positive. Similarly, chromium 3 positive, chromium 6 positive, etc. They form colored compounds. They form colorless compounds, S block or white compound, but transition elements form colored compounds. And there is another typical properties transition metals form. They form stable complexes. So let's discuss the variable oxidation state first. Why transition elements have variable oxidation state? All transition elements exhibit variable oxidation state. This is due to the difference in the energies of the 4s and 3d electron is very similar. It is due to the difference. The main reason is difference in the energies of 4s and 3d orbitals. So 3d electrons are very similar. So therefore after losing their s electrons, so always after losing s electrons, they may also lose d electron. So in this way these elements form ions of roughly similar energy level and similar stability by losing four s and 3d electrons. Hence transition elements, these are the reason due to which transition elements have variable oxidation states. Some of the oxidation states are very uncommon because they are energetically unstable. So the more important oxidation states are written here. So like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So only scandium form, rest of the elements all form +2 oxidation state except scandium, which is only has +3 oxidation state. So I have discussed earlier because and 3d1 and 4s2 3 electrons are removed from the valence shell. So there is no +1 except copper. Copper has only +1 oxidation state, but rest are starting from +2, +2, +2, +2, +2, +2, all have +2. This is the common feature of transition elements except scandium, +2 and +2 and +2, and all have +3 as well. So except zinc has only +2. So zinc and scandium has only +3 while zinc has +2. I will explain this later. So first write down the charges. plus 4 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 till nickel plus 4. And over here titanium has only plus 2 plus 3 and plus 4 oxidation state, but vanadium has plus 5 also, chromium has plus 6 also, and manganese also has plus 5 and in iron there is no plus 4. Sorry, iron has no plus 4, so it has only plus 5, and similarly plus 6 only chromium, manganese and iron has plus 6. Iron has plus 6. So these are and manganese only has plus 7. So there are uncommon oxidation states as well. So for in case of titanium, vanadium and chromium, plus 2 are uncommon. In vanadium plus 3 also uncommon, and sorry, vanadium, not chromium. Vanadium is uncommon plus 3. And manganese plus 3 and plus 4, 5 is uncommon. In case of iron, plus 5 and plus 6 are uncommon, and similarly cobalt plus 4 is uncommon, and nickel plus 4 plus 3 and plus 4 is uncommon, and in case of copper plus 3 are uncommon. So all transition elements except scandium show plus 2 oxidation state. All transition, and these are the main points, please note down. All transition elements except scandium which has plus 3 show plus 2 oxidation state. This is common feature of all transition elements. The first 5 elements from scandium to manganese show their maximum oxidation state. The first 5 elements from scandium to manganese. First 5 elements from scandium to manganese show their maximum possible oxidation state equal to sum of 4s and 3d electrons. As the atomic number increases, the +2 oxidation state becomes progressively more stable than +3 and other higher oxidation states and other higher oxidation states this is due to increasing difficulty of removing 3d electrons across the period due to progressive increase in ionization energy. So hope you will understand all these points regarding the charges of the transition elements, so that why they have variable oxidation state and why they have different stable and which ions are stable and which ions are unstable. So there is another important feature of transition elements like atomic radius, ionic radii and ionization energy. Also ionization energy of transition elements also remain constant. So the reason is this, that the situation in this case of the transition element is rather different from the transition metals to the next. Nuclear charge increases by 1 unit. We know that nuclear charge increases by 1 unit and along with this number of electrons also increases by 1. Increases by 1 unit. So however, the additional electrons enter the inner 3d orbitals and help to shield the 4s electron from the nuclear charge. Therefore, effective nuclear charge remains practically constant across the period. Hence, atomic and ionic radii as well as first ionization energy of the transition elements also remain practically constant. So this is the reason behind this. So as the nuclear charge increases, 1 unit number of electrons also increases. Number of electrons is also shielding electron. This is also known as shielding electrons, which are present in between the nucleus and the valence shell electrons. So shielding electrons also increases, so they cancel the effect of each other. So therefore effective uh, therefore atomic radius, ionic radii and ionic ionization energy also remain constant. So another also important feature is that calcium is group 2 elements is better conductor than the transition element. This is due to due to due to ionization energy of calcium is lower than the ionization energy of all the transition element. Due to its larger atomic size and smaller nuclear charge. Therefore the valence electrons are easily delocalized. Easily delocalized than the transition element. Next reason is, this is first reason, and second reason is density. Density of calcium is also lower than transition element. This allows the delocalized electron to move more freely. So melting point, third reason is melting point of calcium is lower than the transition element. Hope you would understand the properties of electronic configuration and different features of the transition elements. If you like this video, please subscribe the channel and share with others.